Have you ever looked at two things that seem totally different, but you just have this gut feeling that they're kind of the same? Well, today we're diving into a really cool puzzle from math and computer science that takes that exact idea and cranks it up to a whole new level. Okay, check this out. Imagine two people build the exact same car out of Legos. One person uses all red bricks, the other uses all blue ones. Now, they look different, right? But the structure, the way every single piece connects to every other piece, is completely identical. So, are they the same car? It's a simple question, but believe me, it gets way more complicated when we're talking about the foundations of logic instead of toy bricks.
So, yeah, with the Lego cars, we can probably all agree they're basically the same. But what happens when basically the same just isn't good enough? You see, in the world of formal systems, we're talking complex software, mathematical proofs. A tiny error can have massive consequences. Basically the same can be a disaster waiting to happen. You need to be 100% certain.
And that, right there, is the heart of the problem. Your intuition, my intuition, it doesn't count for much here. When you have two different formal structures that seem to act the same way, you can't just shrug and say, close enough. You have to be able to prove with cold, hard logic that their underlying structure is truly, completely equivalent.
All right, let's break this down a bit. To really talk about this special kind of sameness, mathematicians have a very specific and pretty powerful word for it.
That word is isomorphism of types. It's a fancy way of saying that two things, even if they look different on the outside, are structurally identical on the inside. They're like perfect reflections of each other when it comes to their properties and how all their little parts relate to one another. Think of it like this. On the surface, you might be looking at two totally different mathematical formulas, or maybe two chunks of computer code that look nothing alike. But when you dig down and analyze their underlying structure, what's happening under the hood, you find out their logical behavior is identical. The relationships between all their parts are equivalent. That's what it means for them to be isomorphic.
So, how did mathematicians and computer scientists finally get a grip on this whole thing? Well, it wasn't about some clever little trick. Nope, it was about inventing a whole new language to talk about structure itself.
And this is where category theory and type theory enter the picture. Now, don't worry, we're not going to get bogged down in the details. Just think of them as specialized languages that were designed for one main purpose, to describe and analyze structure totally separate from how a thing might look on the surface. They were literally the perfect tools for the job. And having this new perspective was a total game changer. It helped solve these deep, nagging consistency issues in logic. It allowed mathematicians to formally say, hey, let's just ignore the surface details for a second and focus only on the structure, what they call viewing things up to isomorphism. And most importantly, it gave them real, solid methods to finally prove that two things were, in fact, the same. Now, all of this work, this new language, it led to something truly revolutionary. A single, elegant, and unbelievably powerful new rule that could be added to the fundamental rulebook of math itself.
It all started with this really simple but profound question. What if we just cut through all the messy proofs? What if we could just make a new rule that says if two things are structurally the same, if they're isomorphic, then for all intents and purposes, they are equal? What if we could just declare it?
This very idea is the beating heart of a modern field called univalent foundations. It was pioneered by a truly brilliant mathematician named Vladimir Voevodsky. And it's all part of a bigger framework called homotopy type theory, which, get this, connects these super abstract logical ideas to the geometry of shapes and spaces. And the answer to that big what-if question is a rule called the univalence axiom. It's so beautifully simple. It just says that for these kinds of structures, equality is the same thing as equivalence. If they are structurally equivalent, they are identical, period. It takes something mathematicians were doing intuitively for years and makes it a core, foundational truth of logic. So, how does it work in practice? It's incredibly straightforward. You start with two structures, or types, that you've already established are equivalent. Then you just apply the univalence axiom, and poof! The result is that they can now be treated as truly, completely identical within your system. What used to be a long, complicated proof is now just a single, direct step.
So you might be thinking, okay, cool, a new rule. But what does this actually change? Well, the impact is huge. It's about creating stronger, cleaner, more coherent foundations for both mathematics and all of computation.
This matters a lot. For starters, it makes formal proofs way, way simpler.
It gives us a really clean and precise way to handle these isomorphic structures. It's even paved the way for brand new systems like cubicle type theory that give this abstract idea a real, concrete computational meaning. At the end of the day, it's about strengthening the very foundations we build all of our most complex and important logical systems on.
And that kind of leaves us with this one last fascinating thought to chew on. For centuries, mathematicians sort of acted as if equivalent things were the same, but they didn't have the right language to make it a formal truth. The univalence axiom gave them that language. It just makes you wonder, what other obvious truths are out there, floating around, just waiting for us to invent the right language to finally see them?